Hi everyone, welcome back to Math 111. This is Scott. Let's get started. Section 3.2, where we'll be talking about domain and range. All right. First off, let's just put it all out there. What is a domain? What is a range? So the domain of a function is the set of all allowable input values. This is the set of all allowable input values versus the range, I should say, of a function. The range is the set of all possible output values of a function. Alright, well, these are both sets, which means we are probably going to want to do a quick little look at the ways we typically write sets. So, notation for sets. Alright, so sets are collections of values, and there are three main kinds of notation we might use. So there is what's called roster notation, in which we just put a big brace or a squiggly bracket, and we put whatever values we want to include inside it. So this would go like this, and be like 1, 2, 3, something like that. So that, for example, and then the empty set, which is the set that has nothing in it, is either written with just an empty set of braces, or sometimes it's written as a big rounded 0 with a line through it. So that's the first kind. First notation that we frequently use for sets. This is the best kind of notation if your set only has a few elements in it. Now, the second major kind of notation for sets, this is one that's very common, is what's called set builder. Set builder notation. And the way this frequently goes is something like this. So the layout here is it's got a brace, and then it's got usually a variable, and then it's got either a colon or a bar. This is pronounced such that. And then over here, what you have is some conditions. These conditions can be equations, inequalities, all kinds of things. Etc. And then you have the end brace. So an example of this would be something like, let's say you wanted everything except 2. So you'd say the set of all x, for example, such that x is not equal to 2. So this would mean every number except 2. All right, so those are two very commonly used notations, but one that your book is going to want you to use a lot in this particular case is, in the case of domain and range, is what is called interval notation. And the way that looks is as follows. So interval notation, this is the third category. This is best for sets made out of a collection of intervals. Of the number line. And there are 4 possibilities for the basic part of the interval notation, and they go like this. So the basic layout is this. So we have 4 possible ways of writing this. We have square bracket A, B, square bracket. We can have parenthesis A, B, square bracket. We can have square bracket A, B, parenthesis, or we can have parenthesis A, B, parenthesis. And the basic meaning of each of these is the following. So if we have a piece of the number line, and it goes from A to B, then what this would represent is A is included, B is included, and we'd be talking about everything from A to B. So A and B are both included. And then as far as inequalities, this would be the same as saying A is less than or equal to X, which is in turn less than or equal to B. So less than or equal to. Here, what we would be talking about is, again, an interval from A to B, but now the A would be a circle and the B would be a filled in circle. So A is not included, B is. So what that would mean is we have just A less than X less than or equal to B. For the third one, what we would be talking about is the number line going from A to be, the A now would be the one that's filled in, the B would be the one that is not, and so it would be going A less than or equal to X less than B. So this one is not included, this one is included. And then lastly, we would have, in the case of parenthesis, parenthesis, A and B, and now we would have two open circles. So just A less than X less than B. So neither is included. So as an example, let's say that we were talking about a set along the number line that started at 2, went to 7, and let's say that the 2 was not included and that the 7 was. So then the way we would write that is 2 comma 7 parenthesis square bracket. Okay. So this is the basic layout for an elementary interval, but we can elaborate on this a little bit by putting in a couple extra features. So extra features. Extra features. So we can have open-ended. Open-ended intervals. And the way those look is you can have a number A and you can go up to infinity. And what that means is that it starts at A, but it never stops. And similarly, could be open parenthesis A, and then an infinity. And then that would mean that although it starts at A, it doesn't start actually at A, it starts right after A. It's like a little tweezer has plucked that one single point out of the number line, and then it's everything to the right of that. Or we can have it open-ended on the left. So that would be negative infinity to B with a bracket. And what that's going to indicate is it is everything to the left of B and B. And then lastly, negative infinity to B with a parenthesis. And that would mean everything up to B, but not included. So in other words, here we're talking about x is greater than or equal to a. Here we're talking about x is just greater than a. Here we're talking about x is less than or equal to b. And here we are talking about x just being less than b. And then there's one more important piece of the set builder notation. and that is union. Sorry, of interval notation, I should say. Union of intervals. So we use a U-shaped symbol here. We use that to combine multiple intervals into one set. So for example, let's say we had a set of everything below 2 and above 7 with the 2 included, let's say, and the 7 not. Then this would correspond with the interval notation negative infinity to 2. We never include the infinities on the open-ended ones because there is no actual end point that ends there. And then the 2 is included, however. And then we do a U. Nope, it's a mistake. And then 7 to infinity. Okay, so this is how you combine two intervals. Now, back to the actual section that we're talking about here, the domain and the range. So let's start with a graph. So given a graph, the idea here is just look at the quote shadow. The graph casts on the x-axis, that'll be the domain, and the y-axis, and that'll be the range. So, for example, let's take a graph that looks like this. So as our first one, give the domain and range. Let's take a graph that looks like this. So in example A, we're gonna have, let's say it looks like a parabola. And let's say it goes up and then down. Let's say it's got arrows going both to the left and to the right. And here, let's say that it reaches its highest point at a y value of 5. So then, looking at this, for the domain, because of this arrow, that indicates that the graph is supposed to continue doing whatever it's doing all the way to the left. This arrow indicates that the graph is supposed to continue doing whatever it's doing all the way to the right. And so here, the entire x-axis is represented on the graph. And so the domain is actually everything from negative infinity to infinity. So this is, in other words, all real numbers. So sometimes, by the way, this is written just with a blackboard bold R like so. Now for the range, that is not the case. You can see that it goes all the way down thanks to those arrows. However, the highest it gets is the 5. So what that means is it goes from way down at negative infinity all the way up until it reaches 5. 5 is actually included, but infinity never is. Now let's look at another example. This one is going to have some breaks in it. So how about a function that goes like this? So let's say that there is a part of it that is going down and to the left, but then it ends at an open circle right there. And then let's say that there is a closed circle going up from there. And the important x values that we need to know in order to answer this question are going to be that one and that one. And let's say that this is x is negative 5. Let's say this is x is negative 2. And the important y values we're going to need to know are going to be that one and that one. So let's say this one is equal to negative 3. Let's say this one is equal to positive 3. Okay, so now for the domain and for the range, we look at what x values and what y values are represented on the graph here. So for the x values, it's everything below negative 5, not including. But then it's also everything above negative 2. So it's going to be negative 2 to infinity. And these two pieces are joined together into a blessed union by putting that little u. As for the range, we look at the y values. The y values are going to be everything below negative 3, so it's going to be negative infinity to negative 3, like so. Everything above positive 3, so it's going to be 3 up to infinity, like so. And once again, the two pieces are going to be put together with a u for union. And then lastly, let's look at a graph that has a very, very special feature to it. So this is your old friend, the reciprocal function from our toolkit of functions from the previous section. And it's going to be going like that. So it's got one piece going that way, and it's got one piece going this way. This is, once again, the reciprocal function from section 3.1 in the toolkit, and it is, the name for the shape is a hyperbola, similar to a parabola, but different. Now, the way to interpret this is that it doesn't touch the x or y axis. Other than that, though, everything else is in play. So what that means is that the domain is everything except for x equals 0, and the range is everything except for y equals 0. So the way we can do that is negative infinity to 0, not inclusive, and then 0 to infinity, also not inclusive. As for the range, the exact same thing. Negative infinity to 0, not inclusive, then everything from 0 to infinity, also exclusive. This is the customary way to exclude a single value in interval notation. All right, so this is what you do for graphs. You just look at the graph, you look at what x values are represented, you look at what y values are represented, and then you can stitch together the appropriate intervals for each one. But if what we're talking about is not graphs but formulas, then it's a little bit different. So finding the domain. So here's the basic idea on this. What you need to verify is that certain telltale forbidden things don't happen. Those forbidden things are dividing by 0 or taking a square root of a negative. So things that must be prevented. One, dividing by 0. 2, square root of a negative. This also applies to any other even root. But not odd roots, such as the cube root or fifth root, etc. Okay, so these are the two categories of things that must be prevented. And so what we are going to do is look at the formula, look at where it is vulnerable. It's vulnerable at any place where it's dividing by 0, or it's vulnerable any place where it's taking a square root of an expression, because then it might accidentally be a negative value. So those are the two things that we're going to have to try to prevent. So as an example, let's find the domain. First off, let's just take something like this. F of x equals, and now let's say we have 1 over x plus 1. Now you look at the formula and you try to figure out what could go wrong. And the question is, are we in danger of dividing by 0, or are we in danger of taking a square root of a negative? Well, there are no square roots involved here, so that's off the table. The only thing that is involved here is a division, and so what you do is you look at the part that you're dividing by, and you just state that what we need is x plus 1 to be to just not equal 0. Now this you can actually solve the same way you would solve an equation. So if x plus 1 is not supposed to equal 0, then that means x is not equal to just negative 1. Just subtract 1 from both sides. So in other words, we're talking about x just not equaling negative 1. So it's everything before negative 1, and it's everything after negative 1, but not negative 1 itself. So then what that means for the domain is that we are talking about everything before negative 1, oops, negative infinity to negative 1 exclusive, and everything after negative 1, negative 1 to positive infinity, also exclusive. All right. Now, what if what we're talking about is f of x is equal to the square root of 1 minus x? Well, once again, we look for what can go wrong. So here, what do we need? What we need is that 1 minus x is greater than or equal to 0. Well, then what that means is if we subtract 1 from both sides, we have negative x greater than or equal to negative 1. And then if we multiply both sides by negative 1, we'll have x and positive 1. But, here, let's make a little bit more space for ourselves. So we have x and we have positive 1. But because we divided by a negative, what that means is the thing that used to be bigger is now going to be smaller. The thing that used to be smaller is now going to be bigger. So this switches. Because we divided by a negative. Okay, so that switches because we divided by a negative, and so what we're talking about is x is greater than or equal to 1, which means, sorry, less than or equal to 1, which means it's going to be everything to the left of 1. So in other words, the domain here is going to be negative infinity to 1, exclusive and inclusive. Now, continuing along here, what would happen if what we had was, say, g of x is equal to 1 divided by the square root of x minus 3. Well, here, not only do we have a square root, but we also have a division. So what we need here is x minus 3 to be not just greater than or equal to 0, but straight up greater than 0. And because we can't divide by 0. And so it's not greater than or equal to. So it has to be just greater than, which means then x is greater than 3. Which means if we look at it on a number line, we've got 3 and we've got everything to the right of 3, not inclusive. So that means we've got 3 to infinity. Okay, now let's continue with an example where the denominator looks like this. So it's a h of t, so change up the letters a little bit. Let's say h of t is equal to 1 plus t squared. So now you look at this, and you think about what has to happen here. So we need 1 plus t squared to not equal 0. But t squared is always at least 0. So 1 plus t squared is always at least 1. This means the denominator won't equal 0. No matter what t is. So t can be anything. Which means that for the domain, we've got everything from negative infinity to infinity. In other words, all real numbers, also written with what's called a blackboard bold R. Now, let's say what we have is f of x is equal to something like this. Let's say we had the x squared minus x plus 1. So we look through the possible things that could go wrong here, and the list of things that could go wrong would be dividing by 0, but there's no division. Taking a square root of a negative, but there's no square root. And so this actually is safe. So no division. No square root. No issues. Which means the domain is again negative infinity to infinity. In other words, all real numbers. Okay, now one last topic here is what is called piecewise functions. And the idea for this is that you define the function in various sections of its domain. Define the function by several different formulas for several different parts of its domain. The layout for this is like so. So the layout here is f of x is equal to, and then you have a big brace, and here you put a formula, you put a formula, you put a formula, then you have something to separate it, either a comma or the word if or when or semicolon, or sometimes just a big space. And then over here, you have something going on, something going on, something going on. And over here, what you have are the formulas. And over here, what you have are the domains. All right, and then an example of something like this would be something like f of x is equal to, and then here, let's say we have negative 2x plus 1, and then on the other side we have x squared, and we'll say that this is, that this formula is what you get when negative 4 is less than or equal to x, which in turn is less than 0, and this is what you get when x is, so I would say 0 is less than or equal to x, and that in turn is less than or equal to 5. So 0 is the point where the function switches over. So what we have are basically two graphs, one before 0 and one after 0 for the x values. And so what this would look like is as follows. So before 0, we've got formula y equals negative 2x plus 1, and then after 0, we've got a formula y equals x squared. So negative 2x plus 1, that's the equation of just a line, and that's a line that has a negative slope and a y-intercept of 1. So here, because the 0 is not included, we're going to have an open circle, and then it's going to have a negative slope of negative 2, like so. So it's going to look like that. Now, the other piece of the formula here, and sorry, it only goes to negative 4. So if we plug in negative 4, that's going to give us 9 in the original formula, and that tells us how high that dot is. Now the other side of things here is going to be the formula y equals x squared, which is famous. That's it's a parabola, and it's just going to go up and up and up and up and up until it reaches 25. My budgeting of space was a little bit unwise there. Happens sometimes. Oh well. And because this 0 was included on that formula, that's why it's filled in, and it goes up till 5. Now the domain of this particular function is, you'll notice it goes from negative 4 all the way to 5, and everywhere between those there's a part of the graph. So the graph goes from an x value of negative 4 to an x value of 5, and it is completely full between them. So from negative 4 to 5, it's all included. So there's that. Now putting a graph of these is also easiest to do in a computer. So on a computer, my advice here is use Desmos. And I'll show you in a second how to do that on a computer. But we'll use Desmos. You just Google it. And the format is, you just type f of x equals, and then what you have is you do the squiggly bracket, and then you can do -4 less than or equal to x less than 0 colon -2x plus 1, and then you do a comma. This separates the functions. And then what you'll do is the next condition, 0 less than or equal to x less than or equal to 5. This is all on the same line. Colon x squared. And I'll show you how you would actually enter that right now. Is now how we would do the graph in Desmos. So Desmos is a free software that you can either just do on the web, or you can do an app on your phone. And you just type Desmos into Google, and it'll immediately come up, and you can then just click on Graphing Calculator and start graphing. So to do a graph in Desmos is very straightforward. All you do is over here. Should do it in the first one here. Just over here where you have the places to just put in your functions. And so you can do f of x equals. Now to do just a regular function, you would just type in something like f of x equals x squared. And I did the exponent there with the caret and equals. But most likely, if you're doing this on a phone, here, let me show you how you do it on a phone. You would be given a keypad that looks like this, and you would then just be able to do it in the same fashion. So you do f, and then of x equals, and then you could do x, and if it's just squared, you've got a special button for that. If it's some other power, you can do that. So let's say you have that. But let's say we wanted to not do just f of x equals x squared, but we wanted to specifically do the piecewise function that we were just looking at. So to graph the piecewise function, you can now go back to the keypad, find the braces here, and the way you enter this in Desmos is you have to put the condition first. So it's the opposite of the way we enter it when we're writing it down. You put the condition first. So we would say -4 is less than or equal to x, which in turn is less than or equal, sorry, just less than actually, less than 0. And then you would say colon, so you do colon. There it is. Sorry, I don't usually use the keypad thing, so sometimes I forget where things are. But the colon, it was on the letter side. If you do the shift, one side is tilde, one side is colon. So there it was. Okay, so then you would say -2x plus 1 was our formula? Yeah. And then you might want to put a few spaces there. Oh, no, that's not, sorry. Once again, I don't usually use the keypad. Usually I just use a keyboard, but since you're going to be doing this most likely on your phone, I wanted to try to simulate your experience. So okay, so you do the comma, and then you make the next part of the function. You say 0 is then less than or equal to x, which in turn is less than or equal to 5, and then you have to give the formula, and you do that with the colon again, so that's over here on the alphabet side. You do the shift to get the colon off of that one, and then you go back to the number side, and you would do x squared. So there is the formula. So there's the formula entered, and here is our actual graph. Now, the window here is not very convenient for our purposes, and it's very similar to the mistake I made when I was trying to graph it. I didn't really put much forethought into setting up my schedule, or my x and y axis. But here we can go to the little monkey wrench up here, and that gives you the option of adjusting the window a bit. You can also zoom in or out just by doing a pinching method, but here on the x-axis, if I'm only interested in values from -4 to 4, sorry, -4 to +5, then I might as well just put those. So here, -4 to 5. Okay, and then for the y-axis, it was from 0 up to 25 was how high it got. So now if we look at that, it's a little bit tight, so we'll zoom out slightly on it. But now there's the graph. So this is the first installment of the graph that you get from the first formula, and this is the second installment that you get from the second formula. If we had wanted to throw in any other formulas in here, we could have done so. It would have just been something that we can just add to the end here. So you would just do comma, and then you can put in your next formula. So you could say something like 6 is less than or equal to x, which in turn is less than 10, and then the formula, let's say it was equal to 8 minus x, something like that. So we could have a third installment in the formula. I just randomly made one up, and it would look like that. So then you'd have your third piece going that way. What some people do is they actually take the different pieces of the formula and they make those different functions in Desmos, and the advantage of that is then you can make them each a different color so you can see better where the one starts and the other stops. But there's no other advantage to that other than that particular piece. Okay, so that's how you graph a piecewise function in Desmos. And that's the end of that.